In this video, we're going to look at the derivative. Now, the derivative measures the rate of change of a graph with respect to a given variable, which is normally x. We use the limit of the average rate of change between 2 points on the curve to determine the value of the limit, and we do that using what we call first principles. And at a point on the curve, the derivative has the same value. The derivative has the same value as the gradient of the tangent to the curve at that particular point. And that value we call the instantaneous rate of change for that point. So let's have a look at each of these individually. So the average rate of change of a function is normally talked about as being the rate of change between two x values. So we've got an x value of a here and an x value of b here. And the average rate of change is the gradient of a straight line called a secant. So that's this line here. And a secant is a line that joins 2 points on a curve. And so to find the gradient of that line, we use our gradient. So the average rate of change is equal to the gradient. And our gradient is rise over run. So for these 2 points here on our graph, we'll create a little right-angled triangle. This is our rise and this is our run. So our rise is the difference between f of b and f of a. And so we take this top value and we minus the bottom value. And so our formula becomes our rise, which is f of b minus f of a, over our run, which is our b value minus our a value. And this is the formula that we use for average rate of change. So let's look at an example. For f of x is x squared, find the average rate of change of the function between x equals 1 and x equals 4. So you can see I've already written my average rate of change formula, and so I just need to fill in the two values. So I'm just going to sketch a little graph. So you don't actually need to draw a graph, I'm just drawing a graph so that you can see what it is that we're doing. So we're looking for the rate of change between our points 1 and 4, and I haven't drawn this very well, 1 and 4. So we're going to find the gradient of this green line here. And the green line passes through the point 1, and because it's on the curve x squared, so it will be 1 squared is 1, and it also passes through the point 4 something. And so 4 squared is 16, so it's 416, so it's 16 up here. And so what we do in our formula, we're actually going to substitute in f of 4 minus f of 1 over 4 minus 1. Now it doesn't actually matter whether you do f of 1 minus f of 4, f of 4 minus f of 1, as long as these two are first and these two are second. So you can do it. As f of 1 minus. I'll do it in a sec. So what we've got here is 16 minus 1 over 4 minus 1, which is 15 over 3, which is 5. If I did it the other way and did f of 1 minus f of 4, as long as I got the 1 first and the 4 second, we'll get the same answer. So f of 1 is 1 minus f of 4 is 16 over 1 minus 4. So this gives us minus 15 over minus 3, which gives us the same answer as 5. So as long as you get the numbers in the corresponding position, it doesn't matter which order you do it. So that's why you don't need to draw a graph for these things. So the derivative can also be defined as the limit of the average rate of change between 2 points. So I've got 2 points here and I've called them x, and they're going to be h units apart. So this one here is x plus h. So if I do the average rate of change formula for these 2 points here and here, it's going to be f of x plus h take away f of x. So this is our rise, here, divided by our run, which is going to end up being h, but we're going to use the same pattern. Remember I talked about the pattern? So we've got x plus h here, so we'll have x plus h at the bottom. We've got x here, so we'll have x at the bottom. And then x plus h minus x gives us, just on the bottom of our formula, h. And so, as I mentioned at the start, our derivative, we're going to define as either dy dx, let's call it f dashed of x, is our derivative, is going to be equal to the limit as our h gets smaller and smaller and smaller and approaches 0 of that area of the average rate of change formula. So this is often the formula that you'll see for the derivative function. And because we're starting from the average rate of change, we call this our first principles rule. Finding the derivative from first principles, we evaluate this limit. So let's review how you evaluate a limit. Now, in evaluating limits, if you can substitute the value of the limit in and it doesn't create an undefined result, then you can just substitute in and you've got a solution. So I have an example here. I have the limit as h approaches 2 of 2h plus 3. And so what I do is I put this 2 where the h is in the formula and then evaluate. But if the substitution does cause an undefined result, then there's two things that you can do to fix that. The first is to factorise. Normally, one of the problems is that you'll get something over zero. When you try and substitute in, you'll end up with something over 0, and that will get you an undefined. That's the most common one when you're working with limits. If you're working with derivatives, if you're just working with limits in general, sometimes you might need to use algebra to rearrange, but in all of the cases with the derivative, that won't be the case. So let's have a look at how you go about setting out your work for evaluating a limit. So let's find the derivative of this particular function here using first principles. So I'm going to write our first principles formula, and you'll notice that I've got the negative symbol here in bright green, and that's because this is one of the major causes of problems for students when they work out a derivative from first principles, this negative sign here. So we're actually going to take away the whole of f of x. So to do this, we're going to need the formula for f of x, and we're going to need the formula for f of x plus h. So there's two ways that you can set this out. You can start with this formula and have your limit at the front, which is what you'll need if you label it as f dash x, which means that every line that you write until you substitute in that limit has to have that limit as h approaches 0 at the front, and then you'll have other stuff here. The other way that you can do it is to write your formula for f of x plus h minus f of x over h and simplify that, and then evaluate the limit at the end. I'll just finish filling this in. Okay, so I've filled in the two formulas, and so this is f of x plus h. Take away all of f of x. Now you see what that green minus sign was for. So I'm going to expand those brackets out. So this is a perfect square. I'm going to multiply through by this negative 1, then expand this bracket out, and we get this long giant thing here. Now, if you've expanded everything correctly, what you should find is that every term in the numerator that doesn't contain an h should have a matching term so that it cancels out to 0, so that all you're left with on the top line are terms that contain h. So the 3x squared has a minus 3x squared plus x minus x plus 1 minus 1. Everything else has a h in it. So when we rewrite it, it simplifies a lot down, and you can see that there is an h in every single one of these terms. So we're going to take a common factor of h out the front, and then cancel our h's down. And so we've simplified our formula as much as we can. So now we're going to actually find the limit. And so now I write my formula with my limit at the front. So you'll notice that back up here, I just have f of x plus h. I just have that formula, and then I have equals all the way down. So now I've got this limit at the front, and I substitute my values in, and while there is still an h in the formula, I have to write this limit at the front every single time. So this equal sign here means that this line has to be equal to the line up above, which has a limit in it. But once I have substituted my limit in, my limiting value in, so I've replaced the h in the formula with a 0, then I can drop that limit sign at the front. And then I can evaluate it, and then I have finally that the derivative is equal to 6x plus 1. And finally, an exam hint. Unless they specifically say in the question to use first principles, do not use first principles. It's just a waste of time. Use the patterns instead. But if you do have to use first principles, watch your setting out, particularly when you write limit at the front. Remember, it has to be there until you substitute it in. The instantaneous rate of change is the rate of change at a particular point. It's the derivative evaluated at a specific point. So if we use our derivative formula from the previous question, which was 6x plus 1, to find the derivative at x is equal to 3, we substitute the 3, x is equal to 3, into our derivative formula. And so what we've got is the number 19. So this is our instantaneous rate of change. The instantaneous rate of change is also the gradient of the tangent line to the curve at that particular point. So at the point x is equal to 3, so on the graph, at x is equal to 3, the tangent line has a gradient of 19. So the equation of the tangent will be something like y is equal to 19x plus some constant c. And you could work out that c by substituting in the x, y values for the point on the tangent, which is also the point on the line. The final thing to talk about is derivatives, CAS, and the notation that you use in your SACs and in your exams. So I've got a screenshot from the TI Inspire, and I've got different ways of finding the derivative and the limit here. So the first one finds the derivative. The second one is what you get when you do derivative at a point on a menu. So this is at the point x is equal to 3, and you can see we got our answer of 19 as well. And here I've defined a function so that I can use the limit capability of the CAS calculator, which is also under the calculus menu, to find the derivative of our function here. You wouldn't do this very often at all. But I do want to talk about the fact that we've got dy dx notation, which is Leibniz notation. We also have our function notation, which is we use as f of x, and what's called operator notation, which is what your CAS calculator is using here. Now, you need to be aware that these d's in the Leibniz notation are not variables and they can't be cancelled down. They actually are meant to represent the Greek letter delta, which means a small change in y over a small change in x. A small change in y is our rise, and a small change in x is our run. And so it's actually telling you to use the gradient formula for it. Now in the exam, you cannot swap between dy dx and f dashed x. You have to use, if you're given y is equal to in the exam, that means that you need to use dy dx unless you define y as f of x. If you're given f of x in the exam and you're asked to find the derivative, that means that you need to use f dashed of x. Make sure you get these right. If you swap from one to the other without defining anything, you've introduced a new function and it will be incorrect. Make sure you get your notation correct.